Good morning. Okay, so today we're going to do another projectile motion problem. And this one is, I don't think it's too difficult. This one's probably one of the easier ones. So let's read it. At a restaurant, you decide to shoot your sibling with a spit wad using your straw while your parents are busy talking about something you find completely boring. You launch your present with a horizontal speed of 1.2 meters per second, and it reaches its maximum height at 0.50 meters horizontally in front of you. Along with some horizontal velocity, you did impart a vertical velocity to your gift at launch. What was the vertical speed of your spit wad at launch? All right, so you would categorize this as a projectile motion problem. This is because you have an object that's launched with some forward velocity as well as a vertical velocity. So it's like diagonal in front of you instead of just pure vertical. But you also are told that you gave it some vertical speed as well as some horizontal speed. So you're given that horizontal initial speed at launch, but you're not given the amount of vertical speed. You just know that there was some, and you're asked to find it. So that's what we're going to be finding here. The only thing you're really given is that the maximum height of your projectile was achieved 0.50 meters horizontally in front of you. So we're talking about a location of interest. We're given information about a location of interest that is at the maximum height. So anytime you read maximum height in a problem, you want to pull out of your brain that, okay, I always know something special about the maximum height, and that is that at the maximum height, the velocity in the y direction equals 0. So in this case, you have to decide whether that's an initial or a final, but at least you know that the velocity is 0 there. So let's figure out which one it is. If you want to be less likely to make a mistake, you definitely want to draw a picture for these kinds of problems. You get your axes. And when you're drawing projectile motion problems, the standard axis you're going to draw is all in position, so that we have position in the x direction and position in the y direction. So we're essentially kind of drawing a time-lapse photography picture of what is happening. You get the projectile path in space, and any time information you have to place, like, oh, here it was this time and here it was that time, but the time isn't on the axes. So if my point of launch happens here, I know that the velocity initial had some upward as well as forward component. So my v initial is made of a v naught x and a v naught y, and there was some angle here associated with it. The path that happens here, because it had some forward and upward path, this is like kind of tangent-ish to the line of the projectile's path, its trajectory. It's going to come up and down. So it makes sense that it would have a maximum point in space in front of you somewhere. Where that is would be x for that maximum position, and you'll have some height of that maximum position, and we're going to use this as our final position. We have our initial position being the moment of launch, and because we're given information about when it's at its maximum height horizontally, that's going to be another point of interest. It's going to be our final position. So this will be our x final, and it's 0.5 meters, 0.50 meters. So from the point of release, which would be our x initial. We're going to call that one 0 because we're going to set it as 0 so that our final is just 0.5 meters. The distance between here and there is 0.5 meters. This one is our initial position because everything starts there. And then your spit wad follows a path until at a later time it's here. So this will be our final. This is our initial. We know the velocity at that maximum height is 0 in the y direction. So that's going to be our final velocity then, v final y. So v final y equals 0. We don't know y final. We don't know y initial. We could set y initial as 0. We still wouldn't know y final. But we just know this distance. We do know one other thing that I haven't actually put into this picture, which is the horizontal speed in terms of one other thing given in our problem. So that is the x component here. 1.2 meters per second is our x component. So that's the horizontal component. And then we know that gravity points down for all of these kinds of problems. The acceleration in the y direction is minus little g. In my reference frame, I placed my positive horizontal axis up and gravity points down, so that's why it's minus. And then the magnitude of the acceleration due to gravity near the surface of the Earth is, we'll just say 9.8 meters per second squared. Everything else is 2 sig figs, so we only really need 2 sig figs here for our gravity. All right, so now we start to solve. We've filled in all the variables and we need to solve. When it's a projectile motion problem, we're always going to break apart and just write the x direction motion separately from the y direction motion. In the x direction, because I always place my x direction parallel to the ground, it is a constant velocity motion. In our y direction, we have gravity acting, so it is constant acceleration. What am I writing? So there's only one equation for constant velocity. That's easy. We can just write that down in the x direction. X final equals x initial plus v naught in the x direction delta t. This, I'm subscripting v naught x as the initial velocity in the x, but this is also the final velocity in the x and the velocity in the x at any moment because it's constant velocity, so it's not changing. Our final position is the 0.50 meters, 0.50 meters equals 0 meters, plus our initial velocity in the x direction is 1.2 meters per second, and then time, I'll just leave it as delta t. So we can go ahead and solve for the time to get to that maximum position. 1.50 meters equals, divided by, bring our 1.2 over to the other side, delta t. So that that is our value for delta t. And if I plug that into my calculator, I get 0.42 seconds. The meters cancel, and the seconds, which are in the denominator of the denominator, go up to the numerator and become time. So I have the time it takes to get to that maximum height. And in my y direction, I'm going to use one of my constant acceleration equations. So we have 3 of those. And if I just write them right here real quick to reference, then we can look at them. V final in the y direction equals V initial in the y direction plus AY delta t. Y final equals Y initial plus V naught Y delta t plus 1/2 AY delta t squared. Or V final Y squared equals V initial Y squared plus 2 AY delta Y. So we have those 3 to choose from in our y direction because those are all constant acceleration equations. And we need to pick which one will make sense for us. We're looking for the initial velocity in the y direction. That's what we're looking for in this problem. So I'll square that out in green. The initial velocity in the y, that's what we want. It's not, there we go. And there, wait, not that one, that one. All right, and then things we know, I'm going to all square in blue. So that one we do know. We know the final velocity in the y direction is 0. We know the acceleration in the y direction for all of these. It's just gravity. We also know the final velocity in the y direction here. We don't know the maximum height that's achieved, so we don't know y final. Why don't I underline that in red? We don't know y initial, although we could set it to 0, so that one's not as big of a deal, but we don't know those. We now do know time because we solved for it using our x direction information that they gave us. So at this point, as I'm working over here, I might as well indicate that I know it. So when I look at these 3 equations, I would like something that the thing I am solving for to be the only thing that's unknown in the equation, and that's going to be this one. Everything is either blue or green, and there's no red because there are no unknowns that we don't want the answer to. All right, so I'm going to plug in my knowns into this first equation. The velocity final in the y direction is 0. The velocity initial in the y direction is what we're looking to solve for. The acceleration in the y direction is minus 9.8 meters per second squared to 2 sig figs. And the time I solve for here as 0.42 seconds. Solve for v naught in the y direction. Plug that into our calculator. And 2 sig figs, we get 4.1. My seconds cancels with one of those, and I'm left with meters per second. So my v initial in the y direction. So this is the speed. We're asked for the vertical speed, so that's a positive value. Speed is the magnitude. And there you have it. Everything looks good. So there is one more example for projectile motion. And I hope you have a great day.